Okay, this video recording has failed 3 times, so let's hope this works. So we're going to continue on with levers. So if we review from last time, we talked about the 3 classes creatively named by engineers as first, second, and third class. So the main concept here is mechanical advantage greater than 1 or less than 1. So mechanical advantage greater than 1 increases your force. So something like this wrench here will allow you to create a large amount of force to like turn a bolt that is stuck, or if you really want to get something tight. So this increases the amount of force you can have. Whereas a broom is the opposite. That's a mechanical advantage less than 1. That's increasing distance. If you look at this wrench here, if you imagine turning that wrench, your hand moves very far, but that bolt is only going to turn a little bit. So you're giving up distance to increase force. Well, a broom is the opposite, right? If you're moving a broom handle, you're only moving your hand a little bit, but that broom will be sweeping a large distance back and forth. Dust is not heavy, so you don't need to increase force. You want to increase speed. Now it makes it harder to move, but the end of a broom is light anyway, so it doesn't matter. So actual mechanical advantage is the ratio of effort and resistance forces. What does that mean? Well, it's just how many times stronger does something make you, right? And in the case of a broom, let's say that has a mechanical advantage of 0.1 or 1/10. Well, that's making you 0.1 as strong, right? But it's making a broom move 10 times faster or 10 times farther than your hands are. So that's all it means, is how much stronger or how much faster does something make you. Okay, so ideal mechanical advantage. This is a theoretical calculation. It's not based off how the thing actually works. It's based off its measurements and its design, how it should work. It ignores real-world things like friction and things bending, and there's stuff like that makes our things not work perfectly. So if you look at a lever and measure it, you can say, oh, that should give me a mechanical advantage of 10. And if you actually try it and take some force measurements, you'll find out it would maybe be like 9 or 9.5. So it's how things would work in a perfect world. If you've heard ideal before, right? If you close your eyes and imagine for a second your ideal boyfriend or girlfriend. What do they look like? How do they act? Do they have the same interests as you? That'd be your perfect partner. Well, I got bad news for you. The perfect person doesn't exist. Just like the perfect lever does not. It's always less than. Now, if that's depressing that your perfect soulmate doesn't exist, I got even worse news for you. You are not anybody's ideal partner either. But that's okay. We deal with people's shortcomings, right? And we learn to make the best of people. Let's stick to not relationship advice. Let's stick with engineering here. Relationship advice is not my strong suit. So, ideal mechanical advantage. So this is the ratio of distance and effort forces. This looks a lot more complicated than it is. So basically, if you've got a big mechanical advantage, right, like the wrench, you're moving a large distance to move something a small distance. So just like the ratio of those forces, the ratio of those distances, how far you move, will tell you how much mechanical advantage something should give you. Now with a lever, if you follow that all the way around, it makes a circle, and it says it's the effort and resistance, or input and output distances traveled. You can do the math here in the geometry, or you can just believe me that instead of using these distances along the circle it actually moves, it's much easier to just use the distance from the fulcrum. So you can ignore how far it actually goes and just measure from the fulcrum distance in order to do that. It'll make your life a lot easier. Go ahead if you want to do the, if you really want to work through the math of the geometry, I'd be happy to show you why that is. But it makes sense. Imagine if you got a lever that's 10 inches long on the effort and 1 inch long on the resistance. That's a long lever arm. That's going to make you 10 times stronger because it's a ratio of 10 to 1 in a perfect world, ideally. If you measure that, actually, the forces would be a little bit less. Okay, so let's look at some practice problems here. So we've got Sir designs a lever that has an effort distance of 8 inches and a resistance distance of 2 inches. What is the IMA of this lever? So let's draw this out here. So we've got a lever. Now it doesn't say if it's a first or a second class lever. Either one would work for this. I'm going to draw a second class lever. So we've got our resistance here. This is the output. This is the load. This is the thing we're trying to lift. And then our effort is going to be here. I represent that with an arrow. So be careful. This is dr, right? And de, it's not this distance here. You always measure back to the fulcrum. All these measurements go back to the fulcrum. Okay, so we've got de and dr, and we know this one is 2 inches, and this one is equal to 8 inches. So we've got our picture. That's step 0, is draw what it is if there's no picture, and this is just a simple sketch, right? We don't have to get super artistic here. So now let's go to our equation. I guess before that, step 1 is list out our variables. So for all these problems, you will have IMA, DE, and DR. All right, so our IMA, that's what we're trying to find. That's our question. Our effort distance is 8 inches. Oh man, my writing's getting bad. And our resistance distance is 2 inches. So we've got our variables. This is the list, and this is what it's going to be to start every single one of these problems. So now we're going to go to our equation, and don't just start plugging stuff in here. Students usually want to fight me on this and start plugging and chugging. Start with just the equation. It's going to make it harder for you to make mistakes. You will do better if you always, it's an extra step, but write the equation out here. Okay, so now we substitute. All right, so I'm getting ready to write below that. IMA, I don't know what it is, so I'm just going to leave that as IMA. DE is 8 inches, and DR is 2 inches. And our units cancel out, and we're left with IMA equals 8 divided by 2 is 4. This lever is going to make us 4 times stronger, or it should. And notice the units canceling out here. Mechanical advantage is a unitless number. It's just how many times stronger something makes us, so it doesn't actually have any units, just like actual mechanical advantage. Okay, so if we look at the problem here, how much force would he need to lift a 10-pound object? Now, let's assume an ideal mechanical advantage of 4. Let's say the actual is 4. It's making us 4 times stronger. You could reason, well, if I'm trying to lift 10 pounds and I'm 4 times stronger, I would need 2.5 pounds of force. And you're right. And you could go through the AMA equation, and you could solve this using the actual mechanical advantage of 4, and you would find out that that effort force is 2.5 pounds. So that's in a perfect world. In reality, maybe that's 3.9, maybe it's 3.8. We'll get more into that later. For now, we're going to keep it simple. So this problem here, Jason's using a lever to lift a motor out of his car. He needs an IMA of 10. So again, you can use a second or a first class lever for this. Either one will work. Just draw out your picture, list your variables, do all that. Here, be careful. This is, I originally had this as just inches and feet, and then people were confusing that, so I'm like, maybe inches, because this isn't about unit conversion, this is about mechanical advantage. So you're going to find a catapult is trying to increase speed, so this is a mechanical advantage to less than 1, but it's going to make it move faster. So you can kind of think through how much faster would this make us based on the answer you get there. Okay, that's it. That's a lot of information, kind of fast. You can go through this as you need help with these problems. Good luck on this. Oh, and again, this one here, this lever, you can use a second or a first class again. It doesn't matter which, just sketch out whichever you want to choose and think through that. So good luck. Email me if you got questions. Thanks for listening.